last couple of videos, we spent some time defining this new function called an area function. So what I have here is this axis is simultaneously a t-axis and an x-axis. It's a t-axis for the purpose of this curve, which is the graph of f of t, which I'm thinking of as my height function. And then it's an x-axis for this related function, the area function. That's the integral from a to x. So I'm changing. I'm always starting at a, but I'm changing whether I'm going to the right or to the left and how far I'm going. I'm changing what my other endpoint of my interval is going to be. And I'm integrating this height function with respect to t. Okay. So height's a function of t, area is a function of x. What I want to do is just explore the relationship a little bit between the signs of the heights and the areas, and ultimately the derivative of the area. Okay. So I'm going to just record down here the sign of the height function. That's rather easy to pick out. If I just read across from left to right, the height function is positive when it's above the t-axis and negative when it's below. So we start out positive. I'm just going to call this point B. So the height function is positive until we hit B. Now the height function is going to be negative until we hit this point C. Okay. I'm going to mark off A just because that's an important point in these definitions. But I can see the height function is positive from C to A, and then it stays positive. And it stays positive until we hit this point, which I'll call D, at which point the height function becomes negative. Okay. Let's take a look at area now. Okay. Now, it's easier to work with the area when we're integrating left to right, because then the sign of the area matches the sign of the height. So, if I start here and I put x here, the area is going to be positive because I've got a positive base and a positive height. So this area counts as positive. This section of the area over here would count as negative because I'm counting the base as positive but the height as negative. Now, I am not saying that the area function at this point would be negative. It would still be positive because it would be all of this positive area plus just this little piece of negative area. So I'm not saying that the value of a of x at points along this interval will be negative, but that this portion of the area will be contributing negative area to the total signed area represented by a of x. Okay. Now, if I'm integrating this way, now we're counting the base as negative, so the sign of the area over each little subinterval is going to be the opposite of the sign of the height. So this little piece of area would count as negative because it has a negative base and a positive height. The area between B and C would count as positive because it's going to have a negative base and a negative height. Now, once again, that doesn't mean for every point in this interval, the total signed area would be positive. If x is here, I would have this negative area and just a little piece of positive area. Looks like the negative area is bigger, so the total signed area would still be negative. But all of this area is counted as positive when it contributes to the total. And then over here, this area would count as negative because of a negative base and a positive height. Now, what I want to look at now is how the area changes. So I want to look at a prime of x, supposing that the area function is differentiable. So I just want to see, is area increasing, which would make its derivative positive, or is area decreasing, which would make its area negative? Now, let's start at A and go to the right, because that's easier. I meant to call this point D, didn't I? Okay. It's just easier when we're going from left to right. So if I have x here, there's my area. When I'm looking at the derivative, I'm saying as x increases, does area increase or decrease? So if I increase x, I'm adding more of this positive area. The total area would be increasing. And that's going to be the same as long as increasing x, moving to the right, means that I'm adding more of this positive area. So that's going to be the same until we hit D. But once I hit D, now moving to the right, now I'm adding more negative area. And if I'm adding more negative area, that's going to make the area decrease. Okay, let's look over here at what we've got. Now, if we're over here, if we're to the left of A, we're finding the area by integrating from right to left. But when we're asking, does increasing x increase or decrease the area, we're still moving from left to right. We're saying what happens as x increases? Does that increase the area, positive derivative, or does that decrease the area, negative derivative? So if I'm over here, and this is my x, and I increase x, so I move to the right. Now, instead of getting more area, I'm getting less area because I'm decreasing the interval between a and x. But notice over here, I'm getting less of this negative area. So the total area would be getting less negative, which would mean that it's increasing. But then once I pass B, moving x to the right, now I'm getting less of this positive area. If the total area is getting less positive, the area is decreasing. And then once I pass C, now I'm getting less of that negative area. If I'm getting less negative area, the area is increasing. So if I compare the signs here, it looks like the sign of the height function always matches the sign of the derivative of the area function, supposing again that the derivative exists. But it matches the way in which the area is changing, whether it's increasing or decreasing. And if I look at that relationship, I can actually see it's a little bit stronger than just that. Because notice that here, for example, the height function is a lot bigger than it is here. Well, if x is here and I increase x by a little bit, that's going to increase the area by a bigger amount than if x was over here and I increased x by the same amount. So when the height is big, the change in area is going to be big. And when the height is small, the change in area for the same amount of change in x is going to be a lot smaller. So it seems like there's a really powerful connection between f and a prime, the derivative of area. And in fact there is, and that relationship is the fundamental theorem of calculus. So this is the fundamental theorem of calculus, part 1. Now, quick note on that. There are two parts to the fundamental theorem of calculus. Everybody agrees on that. Which one is called part 1 and which one is called part 2? We do not agree on. Textbooks completely vary in which one is part 1 and which one is part 2. So, you need to know both parts. You need to be able to use both parts. I'm not concerned that you know which one is called part 1 and which one is called part 2. Okay. And if I ask you to use a particular part of the fundamental theorem, it should be clear from the task I'm assigning you which part is relevant. But I think especially since this is a community college and a lot of you are going to be transferring to four-year schools, it's important that you know that which one is called part 1 and which one is called part 2 isn't set. So it's entirely possible that you'll be taking an upper division math class at your transfer institution, and the professor will refer back to part 1 of the fundamental theorem of calculus. And she or he will actually be talking about what you learned as part 2. Okay? So the numbering isn't consistent, and it just varies by from textbook to textbook and professor to professor. So you just have to ask, which part do you mean if it's not clear? Okay. So what this says is, if, and I'm going to phrase this just a little bit differently than the textbook, but I'll point out the differences. If f of t is continuous on an open interval containing a and x. Okay. Then a of x, which is the integral from a to x of f of t dt, is continuous on that interval and, more importantly, differentiable on that interval with the derivative of a of x equaling f of x. It just equals the height, but instead of evaluated at a t value, it's the height evaluated at x, at the variable for my area function. Okay. All right, now the way the book phrases things is rather than an open interval containing a and x, they talk about this closed interval from a to b. Obviously, that's going to contain a, and then they say, okay, the function's going to be continuous on that closed interval and differentiable on that open interval. So x would have to be somewhere in here. And then they say the same thing is true if you had an interval instead from b to a. I'm just trying to sort of kill two birds with one stone and not say x has to be either to the right or to the left of a. What's missing from my statement, though, is that the function would be continuous at a even if a was an endpoint of the interval. An open interval, remember, is one that we would describe with parentheses, not including the endpoints. If the function, if a or x is the endpoint of a closed interval, my area function is still continuous, but it might or might not be differentiable. Okay. But pretty much, if I'm dealing with a height function like f of t here was continuous everywhere, so the area function is going to be continuous and differentiable everywhere, and I've got this really powerful relationship between the derivative of area and the height function. And it looks really wonky when I write it all out. The derivative with respect to x of the integral from a to x of f of t dt. That's just my definition of the area function. That derivative is f of x. Now, it made sense geometrically. If the area was changing, whether the area was increasing or decreasing and how quickly was really determined by the height function, whether that was positive or negative and whether that was big or small. So the rate of change of area is the height function, is really what this is saying. Notationally, it looks incredibly intimidating. But basically, it says, hey, if you're integrating an area function like this, you're going to get the height function. But since area is a function of x, there's no way its derivative could be a function of t. You're going to get that height function, but evaluated at x, at that limit of integration. All right, so in the next video, we'll talk a little bit more about the significance of this and then practice using it.